Good morning, everyone. My name is Chen. I'm a second-year master student at CBE who is graduating this semester. Today, I'm very happy to present to the industry partners, including my future colleagues from WSP. So my topic today is on-the-floor air distribution design tools. A quick overview of the project. So CBE has developed an underfloor air distribution design tool in 2010, and it is publicly available online. During the same time, Purdue University also developed another simplified design tool, which is within the ASHRAE Research Project 1522, and it is available to ASHRAE members. So the objective of this particular project is first compare the two UFAD design tools, and then implement the new capabilities into the CBE UFAD online design tools. So my presentation today will start with the comparison work, including the feature comparison and also a numerical comparison, which will assess the accuracy of the two tools. And second, we'll introduce you the new stratification model we developed based on the diffuser performance testing data. And at last, I will show you an example to the updated CBE UFAD online design tool. So the biggest difference between the CBE UFAD design tool and ASHRAE tool is the capability to predict the UFAD cooling load. So the cooling load for UFAD system and the typical well-mixed overhead system are different. And you can easily get the cooling load for overhead systems from the common load calculation programs. And then the CBE tool is able to transfer this overhead cooling load to a UFAD cooling load. However, for the ASHRAE tool, it requires users to input the UFAD cooling load directly, which means you have to get it from like advanced energy simulation program like Energy Plus. Second, the stratification model that CBE tool uses is developed based on the full-scale experimental testing database. And the ASHRAE tool is developed based on an extensive CFD simulation database. Third, the CBE tool provides a temperature at the thermostat height, which is 48 inch, but ASHRAE tool doesn't. And CBE tool can specify 4 plenum configurations. ASHRAE tool can only specify 1 plenum configurations. But ASHRAE tool can give you the result of air distribution effectiveness. The current the first CBE tool does not have this capability, but it is implemented in the newer version. Speaking of thermal stratification profile, one thing I want to point out is that unlike well-mixed overhead systems, so the temperature at the thermostat height doesn't represent user's thermal comfort anymore. Instead, the average temperature in the occupied zone does. So both of the two tools use the average temperature to represent occupants' thermal comfort, but CBE tool provides the temperature at the thermostat height level so that the users know how much you should set the thermostat. And also, ASHRAE standard 55 requires that the temperature difference between your head and ankle level should be less than 5.4 Fahrenheit degrees. As I mentioned before, in terms of the plenum configuration, CBE tool can specify 4, including series and reverse series, independent and common. Which is really important because different plenum configurations can impact the air temperature distribution in the plenum. I'll take a series plenum as an example. As you can see, as the air travels from the interior zone to the parameter zone, it rises up from 60 Fahrenheit degrees to 64 Fahrenheit degrees. However, for the ASHRAE tool, you can only specify 1 plenum configuration and also run 1 zone at a time, but you can run both parameter zone and interior zone at the same time in the CBE tool. Speaking of diffuser type, both of the two tools have the swirl diffuser in the interior zone and the VV directional diffuser in the both interior and parameter zones. So the difference is in the linear barrier diffuser. So the one CBE used is users customized length by 8-inch width. The one the ASHRAE 2 used is a fixed dimension, which is 16-inch by 8-inch width. So that's the feature comparisons. We also did a numerical comparisons in order to assess the accuracy of the two tools. So we combined the database from the CBE and the ASHRAE database, and then we feed each case in the database to both of two tools, and then compared the predicted results. As you can see here, this graph shows the comparison results. X-axis represents the measured ankle temperature from the database, and y-axis represents the predicted value from two tools. So the diagonal line represents the perfect prediction model. And the red dots are the results from the CBE tool, and the blue dots are the results from ASHRAE tool. Here we choose MMRE, which is an index to assess whether a model is a good prediction model or not. And typically, a model with MMRE less than 25% is considered to be a relatively good one. As you can see here, we can conclude that both of the two models have really comparable and very good accuracy, because it's far less than 25%. As I mentioned, we extended the CBE database by adding the database from the ASHRAE. And based on this larger database, we developed a new stratification model. Here, taking the interior VV directional diffuser as an example. So this black line is the old model developed only based on the CBE database, which is the black dots. By adding the data from the ASHRAE database, which here shows as blue dots, we developed this red line as a new prediction model, which better describes the correlations of the thermal stratifications. So you may wonder, okay, we have this new model, so how much difference will make in terms of the temperature stratification prediction, right? Now I'm going to show you a case at this point to show you how much the temperature difference will make between this old model and the new model. So we give same input to the old and the new model, and we use the VV directional diffuser in this interior zone. And this graph shows the stratification profile with temperature on the x-axis and the height on the y-axis. As you can see, as height increases, the temperature goes up. And the difference is actually quite large, because the temperature between the head and ankle could be as much as 2 degrees in terms comparing the old and the new models. So we can imagine if you use the set point from the old model, it will result in the overcooling of the space, so it will also bring the discomfort to the users. So one thing I want to mention about that, we developed this new model, right, and then we implemented it into the CBE UFAD model, UFAD design tool. And one thing I want to mention is this diffuser type, that we changed the drop-down menu from the pure text-based, and now you can see the diffuser pictures and also those short descriptions of the diffusers to help you better select the diffuser. And also, we added one more diffuser type to the parameter zone, which is the linear barrier diffuser from the ASHRAE database. Okay, now I'm going to show you an example of to illustrate how users can use this design tool to answer this question: how many diffusers should be used to achieve the acceptable thermal comfort and also stratification in the UFAD systems? This is the user interface of this UFAD cooling load design tool. It has 3 panels. First is the input, as shown here. And it has a results panel where you can see all the calculation, predicted results. But one thing I want to mention here, we added one more units toggle where you can just click this button and have transfer from between IP and SI unit very easily. And the third panel is the visualization part. We presented the thermal stratification profile in these two, both interior and parameter zones. This is the case we're going to use for this example. It is a typical office layout with 5,000 square feet, two zones, both interior and parameter zones. So for the interior zone, we use a swirl diffuser, and for the parameter zone, we use the linear barbell diffusers. And it is a series plenum, so there's going to be temperature rise when it enters to the parameter zone. Right? And there's 20 people in this in the interior working in the interior zone, and this is a typical design cooling load for overhead system for this office. In terms of the number of diffusers, we're going to start with 10 diffusers in the parameter zones to see what's going to happen. So after we get all those inputs done, we hit the submit button, and what would happen? So it says the design conditions that you have entered into the tool may result in reverse stratification. What does it mean? So it means actually the linear barbell diffusers are throwing the cool air up to the ceiling, which makes the air temperature, return air temperature, maybe lower than the head and ankle temperature. So it says it has that negative energy and indoor air quality impact, right? So how are we going to solve this situation? So we can either increase the number of diffuser or we can reduce the cooling load in the parameter zones. So if we hit OK to see the calculation results, you're going to see this. Yes, in the parameter zone, it does have this reverse stratification, and we don't want that. We don't want that. So from the feedback of the tool, we're going to increase the number of diffusers from 10 to 18 and see whether the problem will be solved. As it showed here, yeah, we solved the problems, and we have 1.5 Fahrenheit degrees of stratification, which is not that bad in terms of the parameter zones. So we fixed the problems in the parameter zone. Now we're going to look at the interior zone. We start with 13 swirl diffuser in the interior zone, and we're going to let's see what the results. So we have 2.2 Fahrenheit degrees of stratification, which is good. But one thing we notice here, the airflow rate calculated per diffuser is 100 CFM, which is more than the nominal value, which is 75 CFM per diffuser. So we don't want that happen. In order to solve this, we add a little bit more diffuser. We add 4 more diffusers. And then we had a little bit more, one Fahrenheit degree more stratification. And also we reduce the airflow rate per diffuser to the nominal value. But as a designer, you want to have more flexibility. Let's say, in case there's like the cooling load is very high some days, you increase the supply airflow rate, and suddenly all those airflow rate will not exceed each diffusers. So you want to have more flexibility. We can add a little bit more diffuser. At the same time, each user can have control of their diffusers to create better thermal comfort. Yeah, that's the end of my presentation, and I would like to take any questions. Thank you.